Welcome to our presentation of Auto-Validate, which makes unsupervised data validation easy. I'm Ji from University of Michigan. This is a joint work with Ye He at Microsoft Research. Complex data pipelines are everywhere today, with diverse use cases, like in ETL, BI, ML. Here are some concrete examples of data pipelines from these products, respectively. And each of these would consist of data processing steps that consumes input data from upstream and produce output data for downstream uses. A lot of these pipelines are actually recurring on a regular basis. For instance, they may be rerun hourly or daily. This is common because you want to regularly refresh your BI dashboard and retain your ML models. However, data quality issues can creep in over time due to schema drift, data drift, etc. Existing solutions to validate data in recurring pipelines include Google's TensorFlow Data Validation, or TFDV, and Amazon's DQ, which we will review next. Both Google's TFDV and Amazon's DQ propose their own convenient domain-specific language for developers to declare data validation rules or constraints. On the left is an example from Amazon's DQ. Here, developers add completeness and uniqueness constraints on some columns with the declarative language. Google's TFDV on the right works in a similar manner. This is a big improvement over ad hoc data validation scripts, but still require developers to manually define constraints one column at a time, which is hard to scale to large numbers of tables and columns. Our aim is to automate data validation, and in this work, we will be specifically focusing on stream-valued data. We crawled 6 million data columns from a large production data pipeline system. We found that a large fraction of these columns have homogeneous machine-generated data produced from the same underlying programs. In these examples, the first case is machine-readable entity IDs for Microsoft knowledge base entities. The second case is beans as delivery status message, etc. As you can see, each of these machine-generated data formats encode specific semantic meanings, and machine-generated data like this are very common, accounting for 40% of columns we sampled. The key question we ask is whether we could automate data validation for such machine-generated stream-valued content, saving the effort of manual validation constraint generation. Naturally, a simple form of validation is to use data patterns. Given the column C, we want to infer the pattern of the underlying domain of C, PC. We could then validate data arriving in the future in the same pipeline using the inferred pattern PC and raise alarms if violations are detected. This data validation problem may look similar to classical data profiling problem, such as Potter's wheel, but both will produce data patterns. The key distinction here is that the two problems have very different goals. In data profiling, a succinct pattern is produced to summarize only the observed value in a given column C. The column shown below, data profiling generates a detailed pattern which summarizes the fact that all given values in the column are for September 12, 2019 at around 9 o'clock. This is great for data profiling because you don't have to inspect all values in this column. With this process pattern, you know what values are being represented in the column. Now in data validation, having such a process pattern is problematic because your data arriving in the future in the same recurring pipeline will not be for 9 o'clock anymore. If we were to use a very specific pattern from data profiling, we will likely produce a lot of false positives for data validation use cases, analogous to overfitting in ML. Instead, we want to produce a suitable pattern that can describe values in the underlying domain of the data column that can generalize to the content may arrive in the future. In this particular case of timestamps, as humans we know what a good pattern should look like, but in general, this is challenging by only looking at one input column C. So in addition to this given input column C from a recurring pipeline, for which validation pattern needs to be generated, we look at background corpus of tables T, which have related tables crawled from other pipelines in the same pipeline system or data lake. Our goal is to infer a suitable validation pattern that can generalize to the future by looking at related examples of data holistically. At a high level, We have two conflicting goals here. One is to ensure that we raise as few false alarms as possible for high precision, and at the same time, we want to catch as many issues as possible for high recall. We identify two subproblems here. First, we need to generate the candidate data validation patterns, named as hypothesis patterns. And second, we determine the best fit pattern among the hypothesis patterns by cross-referencing the tables in the background corpus T. We will elaborate the ideas in more details. First, we leverage a pattern language for hypothesis pattern generation. On the right is the generation hierarchy of the pattern language we picked, amenable for inference. This language is a simplified version of regular expression, which allows constants and atoms of fixed length and variable length. For data column C, a tokenization process splits values in the column into tokens. For each token, a set of generalized variants is generated. The combinations of variants of each token then form the set of hypothesis patterns. For the timestamp column shown below, if we enumerate all possible patterns by doing a simple cross product of possible pattern generalization across all these tokens, we get 3 billion candidates for this simple data column. The pattern language can be instantiated differently. This is the one we use by default. Then, given the query column C and the set of hypothesis pattern H inferred for it using the pattern language, how do we decide which ones are the good ones for data validation? We leverage the data corpus T collected from the same pipeline for quality checks. If a pattern H is a common pattern, such that many columns in the data corpus T follow the pattern substantially with high quality, we reckon the pattern as a good validation pattern for C. Here we regard the quality as the purity, where the more the values in the column match a pattern, the higher the purity of the column against the pattern. If many columns in the data corpus following the hypothesis pattern H are pure, then H is a good pattern for C. For the example below, more columns in T substantially matching H4 are purer than those matching H1 and H2, since H4 is more general than H1 and H2 for columns with timestamp information, incurring less non-matches comparatively. With the preliminary pattern language, we formulate the problem by describing a basic version of auto-validate for ease of illustration. Before going into more involved algorithm variants that use vertical cuts and horizontal cuts that deal with data composed of multiple domains and ad hoc values respectively. We formulate data validation as an optimization problem. Given the input query column C and the background corpus T, we need to produce a validation pattern H, such that H expected to have high purity or low impurity, but can still catch many quality issues. Specifically, we introduce an FPR minimizing version of data validation called FMDV. Here, FPR of H is the expected false positive rate of H, estimated using T, which has to be lower than a given target threshold R to avoid false detections. And the coverage of H is the number of columns in T that match H, which has to be greater than a given threshold M for H to be a valid domain. In the previous discussion of pattern language, we showed that approximately 3 billion hypothesis patterns can be generated for a single timestamp column. If we were to check each of the hypothesis patterns against all columns in T, of which each may have over billions of patterns, the computational cost is massive. We adopt an optimization technique by separating the offline pre-processing from online querying. During the offline stage, we pre-compute the index of possible hypothesis patterns for efficient online search in 2 steps. In the first step, for each pattern P of some column D in T, we pre-compute its local impurity score FPR. Since P may be hypothesized as a domain pattern for some query column C in the future, for which this D can provide a piece of local evidence. Let P be the space of possible patterns in T. For the second step, we pre-compute FPR for all possible patterns in P on the entire T by aggregating local FPRs for all columns substantially following the pattern. The coverage of all P can be pre-computed similarly. The result from the offline step is an index for lookup that maps each possible P to its pre-computed FPR and coverage values. We know that this index is many orders of magnitude smaller than the original T. For instance, a 1 terabyte corpus T yields an index less than 1 gigabyte in our experiment. Here we show an example for truncated timestamp columns for the two steps. At online query time, for a given query column C, we enumerate its hypothesis patterns and use the offline index to perform a lookup to retrieve FPR and coverage scores, without needing to scan the full T again. They are then checked against the coverage and FPR's constraints. The patterns minimizing the average FPR is the good pattern we are looking for. This indexing approach reduces our latency for query column C from hours to tens of milliseconds, which makes it possible to do interactive human-in-the-loop verification of suggested rules. By careful examination of the crawling data, we found that data values of some columns have structure concatenated from atomic domains. In such cases, a straightforward lookup using the basic version of AutoValidate may fail due to two reasons. For some cases, the composite domain may not have enough coverage in the data corpus, failing to check against the coverage constraint. In some other cases, there are too many tokens split by the pattern language, and thus failing the hypothesis pattern generation process in offline indexing due to token limit constraint, a hyperparameter restricting the number of variants permitted for each token, to avoid an explosive number of hypothesis patterns. A natural approach to complex query column C is to vertically cut it into subcolumns. Patterns for each subcolumn can then be generated in turn using FMDV. The benefit of this divide and conquer approach is that each subdomain is likely well represented in T, allowing them to be reliably inferred from T. For the vertical cut version of AutoValidate, we generate a space of subquery column lists by cutting values in the query column C into subcolumns. For the object function, instead of minimizing FPR for the column, we minimize the sum of FPRs for the subcolumns. We adopt the dynamic programming approach for efficient subcolumn hypothesis pattern generation and FPR evaluation. So far, we assume the query column C to be clean with homogeneous values drawn from the same domain, since they are generated by the same underlying program. While this is generally true, we observe that some columns can have ad hoc special values, for instance, denoting null and empty values, that do not follow the domain pattern. For some other columns, we spot data from two domains, for instance, a data column has two date-time formats. The intuition is to rewrite the object function to select a subset of hypothesis patterns that cover the majority of values in C. This is an NP-hard problem, assuming key patterns represented in C. For the simplest case, we assume K equals to 1. We then try to find the dominant pattern H such that the majority of values follow C with a few exceptions, constrained by the non-conforming tolerance parameter, theta. The default value of theta is 95%, allowing up to 5% values to be special. We then perform a hypothesis testing to validate the constraint. We compare our proposed approach, shown in the red circle, with many existing techniques from data profiling and data validation. We sample 1,000 columns from our production data, and for each column, we use the first 10% as training data for different algorithms to suggest a validation constraint. And then the suggested constraint will be tested on the remaining 90% of values in the same column to evaluate precision and recall. As you can see, in this precision recall chart and on this benchmark using enterprise data, our proposed approach substantially outperforms all alternatives in terms of precision and recall. We have many more experiments on other benchmarks, such as open data from the government domain, where auto-validate has a similar performance. We also evaluated the performance of auto-validate in terms of sensitivity, runtime efficiency, and conducted a user study to evaluate the human benefit of adopting auto-validate for data pattern validation, as well as a case study using Kaggle datasets. We will show next the sensitivity and runtime evaluation. We evaluate the sensitivity of auto-validate and its variance against hyperparameters in terms of precision recall, namely FPR threshold, coverage threshold, token limit, and non-conforming tolerance. We found that auto-validate and its variants are sensitive to small FPR thresholds and relatively stable against changes in coverage, token limit, and non-conforming tolerance. In terms of efficiency, we evaluate the average latency to process one query column C or columns in the benchmark. The figure below shows that offline indexing optimization can largely reduce the processing time. Auto-validate and its variants tend to have comparable runtime, all of which runs 2 orders of magnitude faster than other baselines. We have shown that the importance of data validation has been recognized by recurring pipelines composed of data operations and ML operations. Prior work from Amazon and Google have developed declarative domain-specific language which makes data validation easy compared to ad hoc validation scripts. However, they cannot eliminate human effort in manual generation of the data validation rules. Our work of auto-validate is a promising solution for automatic data validation rule generation, which has recently been shipped in Microsoft Azure Purview. We think automatic data validation is a promising area which remains to be explored by future research. That's it. Thank you for listening, and I'm happy to take any questions.